Let's say I have some sequence of points, p1, p2, p3, and so on, all in the domain of some function f, and let's say that this sequence of points converges to some point p, also in the domain of f. Then what can I say about the sequence of points f of p1, f of p2, f of p3, and so on? Does this sequence of points converge to f of p? The answer to this question is yes, under the condition that f is a continuous function. But we can make an even stronger statement. We can say the following, that f is a continuous function at the point p if and only if, for every sequence of points p1, p2, p3, and so on in the domain of f that converges to the point p, we have that the sequence of points f of p1, f of p2, f of p3, and so on converges to the point f of p. Well, how can this possibly be true? Well, we'll prove it, first proving this direction of the if and only if statement, and in the next video, we're going to prove the other direction of this equivalence statement. And remember, to prove this left to right direction, we first take the statement on the left to be given, and we prove the statement on the right. So let's do that. Let f be a function that maps from x to y, continuous at the point p. And in order to prove this statement on the right, we need to first take any sequence of points in the domain of f that converges to p. So let p1, p2, p3, and so on converge to p. So this is just any sequence in x that converges to p, and we prove that the sequence f of p1, f of p2, f of p3, and so on converges to f of p. So take a second and try to prove that this sequence converges to f of p, and make sure to leverage the fact that f is continuous at the point p. So I'm assuming you've given it a try. So one way to show that this sequence right here converges to f of p, and this is by no means the only way, but one way is to use directly the definition of convergence. So what I mean by that is this. We need to show that for any epsilon strictly greater than 0, there exists a capital N in the positive integers, such that the distance from f of p and f of pn is strictly less than epsilon for all n strictly greater than n. So every term in the sequence that comes after the term, the capital Nth term, has a distance away from f of p strictly less than epsilon. We are directly using here the definition of convergence, except we're plugging in, you can think of it as plugging in this sequence right here to the definition of convergence. So if we can prove this, then we've proven that this sequence converges to f of p. But remember, I said before, we want to leverage the fact that f is continuous. So let's rephrase what it means for f to be continuous at the point p. And I'll write that in yellow here. We know since f is continuous at the point p, then by definition of continuity at a point p, we know that for all epsilon strictly greater than 0, there exists a delta strictly greater than 0, such that if x is some point in the domain of f, and x is a distance away from p, x is a distance away from p strictly less than delta, then this implies that the distance between f of p and f of x is strictly less than epsilon. So take a minute and think about how we can use the fact that the function f is continuous at the point p to prove the convergence of this sequence. And I'll give you a hint. If we go to our picture here, we know that for any epsilon strictly greater than 0, there exists a delta strictly greater than 0, such that if we have some x, it's a distance away from p strictly less than delta, x is a distance away from p strictly less than delta, then that implies that f of x is a distance away from f of p strictly less than epsilon. So I'm assuming you've given it some thought. So the key crux move that we're going to use is the fact that we're always going to be able to find terms in this sequence right here, the sequence P1, P2, P3, and so on. We're always going to be able to find terms, and in fact an infinite number of terms in this sequence whose distance away from P is strictly less than delta for any possible delta. So we're now ready to put all of this together to finally prove our statement, to prove that this sequence converges to f of P. So we're going to say, let epsilon be any epsilon strictly greater than 0. So this is just any old epsilon strictly greater than 0. We know, because f is continuous at the point P, that there exists a delta strictly greater than 0, such that the following implication holds. If x is in the domain of f, and x is a distance away from P, strictly less than delta, then that implies that the distance between f of P and f of x is strictly less than epsilon. This is just using the definition of continuity at the point P. But check this out. We know, since the sequence P1, P2, P3, and so on converges to the point P, we know by definition of convergence that there exists a positive integer n such that the distance between P and P sub n is strictly less than delta. This delta right here is strictly less than delta for all n strictly greater than n. But check out what this means. Remember, because of this implication right here, if we have a point, say P sub n, that's a distance away from P strictly less than delta, then that implies that the distance away from f of Pn and f of P is strictly less than epsilon. So check this out. Check this out. The distance away from P and P sub n is strictly less than delta for every n strictly greater than n. So that implies that the distance away from f of P, the distance between f of P and f of P n sub n, f of P sub n, is strictly less than epsilon for every n strictly greater than n. And we have proven exactly this statement right here, because we wanted to show that for any epsilon strictly greater than 0, and this is any epsilon strictly greater than 0, that there exists an n in the positive integers, and we know that there exists an n in the positive integers because of the convergence of P1, P2, P3, and so on, that sequence P1, P2, P3, and so on, such that the distance between f of P and f of Pn is strictly less than epsilon for all n greater than n.